Folks, in this video, we are going to be talking about one of the most consequential experiments of the early 19th century. This is Young's double slit experiment by Thomas Young. This video will deal with the concept behind the experiment. The next video will deal with some quantitative predictions of the experiment. So the main question we want to answer here is, I've been telling you light's a wave. How do we know that light is a wave? Have you ever seen electric fields go up and down like that? And I haven't. So how do we actually know that it's a wave and not just a particle, a beam of light particles bouncing into your eye, and that's what sight is? How do we know? The answer is Young's double slit experiment. But let's go through the storyline of Young's experiment. So here's the setup. We have a floodlight. He didn't use a floodlight in 1801, but we've got light coming in. We have two slits, slit 1 and slit 2, labeled S1 and S2. And then otherwise we've got a barrier. So light can only hit these two slits. And we have a screen over here where we can observe the light that passes through those two slits. So we've got barrier with two holes in it, observation screen over here. That's what's going on. The results of this experiment will be different if light is a particle compared to if light is a wave. And so, since this experiment gives different predictions for those two different hypotheses, we can use it to figure out which light actually is. So, if light's a particle, that's our diagram on the left. The beam of light particles are going to be incident on our double slit screen, and only the ones that pass through the holes are going to go straight through. In our optical screen, you're going to see two bright lines that correspond to the two slits, right? This bright spot corresponds to this slit. This bright spot corresponds to the bottom slit. If light's a wave, however, it will diffract and bend around those two slits. And we get this interference pattern that we are going to spend several more slides talking about. I know it looks kind of complicated right now, but you have this incident plane wave that then spreads out as spherical sources, and on your viewing screen you get alternating bright and dark spots, not just two bright spots for the two slits, but several bright spots. Let's talk about that and why. So, interference pattern. Why do we see, that's what that alternating bright, dark is called, an interference pattern. Why do we see that? So, light wave comes in through slit 1, light wave goes in through slit 2. That's what's going on. And let's look at different points on the observation screen. So, let's look at first this point on the observation screen. We can see that the two light waves that pass through constructively interfere there. Since they constructively interfere, we're going to see a bright spot there. And that's what this red bar represents. Let's look at two different points here, or a different point higher up on the screen. At this point higher up on the screen, we can see that the trough of the bottom wave lines up with the crest of the top wave. This is where our path difference is half of a wavelength. Go back to the previous video on wave superposition if you want to review on that. But the idea was that if we're a half integer multiple of the wavelength with a path difference, let me back up. The idea was that if the difference in the paths between our two waves was a half integer multiple of the wavelength, then those waves are out of phase and you get darkness. And so we're going to see, let me get rid of the bubble. So we're going to see dark spots at the point where the crest meets the trough. I'm going to represent that with the black bar here. Let's look at a different point on the screen. This wave comes through, this wave comes through. We see that at the location where the screen is, the two troughs line up. We get constructive interference. We get ourselves a bright spot. The same thing happens if we look further up this path. We get alternating bright, dark, corresponding to alternating Waves line up, they don't line up. Waves line up, they don't line up. The similar pattern occurs on the other side. This whole thing is symmetric. So that's why you see that interference pattern. It's the two waves are interfering with each other through wave superposition and constructive and destructive interference at different points along the screen. Of course, this occurs at all points in space at the same time. These are two-dimensional waves. We're not just going to look point by point. In reality, it looks something more like this, where you have on the left the plane waves coming in, and then on the right you have two separate circular waves. And the result of this, when you add those two circular waves together from the left image, you get something like the right image. And the superposition is now shown, and we can see we have bright spot and then dark spot and then bright spot and then dark spot and then bright spot, and on the other side we've got dark, bright, dark, bright. The two diffracted waves add to give alternating places of total constructive and total destructive interference. And in this red rectangle here, that's the observation screen. That's what you would actually see if you ran this experiment. You'd see a pattern of light that looked like what's in the red rectangle. So, continuing on our story now, we now know what light will look like if it's a particle when it passes through a double slit experiment. That's on the left. And we know what light on an observation screen will look like if light is a wave and it diffracts and interferes with itself. That's the alternating bright dark on the right. So, which actually happens? It's the one on the right. Spoiler alert, that's why we're talking about all this. It's the one on the right. The next slide here has both an animation and an actual photograph of the results of a Young's double slit experiment. So on the left, this is what your experimental setup might look like. Light source, two slits here with a barrier. Then over here is the screen where you see the resulting interference pattern. And then on the right is an actual photograph of the results of a Young double slit experiment. So light is a wave. Remember, the laser light we're seeing here on the right, if light were a particle, we would only see two bright spots, one corresponding to where each of the slits allowed particles to pass through. But since wave can diffract and spread out through the barrier, and because it can add and subtract with itself through wave superposition, we see alternating bright and dark spots instead. I do want to mention one thing actually before I conclude the video. Is like right now my mouse is on a dark spot. That dark spot isn't due to the absence of incoming light. That dark spot right there is due to the fact that there are two light waves coming in that happen to destructively interfere. So this is a point where light plus light equals dark, because the waves are out of phase with each other and they destructively interfere with each other, which is just wild. That can happen. All right, so that's our qualitative introduction to Young's double slit. Next video, we are going to look at quantitative predictions for this experiment.